Well, good morning, everybody. I'm going to be the exception. I'm going to speak English rather than Korean. My talk is going to be maybe a little bit different than the previous one and the future one. And I'm going to begin. I was a little bit puzzled by the title of the day, The Dream for the Nobel Prize. And the issue is not the dream. The issue is to materialize the dream, how you materialize the dream. And the other issue is whether the Nobel Prize is a target by itself. It has never been a target for me. I mean, it's not that I decided that I'm going for it. And I think that the target should be, of course, making breakthroughs in science and technology, improving the lives of people around you, in your own country and in the world. And the Nobel Prize is some kind of an accolade that people invented 120 years ago. And I do realize the desire of Korea to be part of this one, because Korea is so much advanced. The economy is one of the strongest in the world. The universities are leading in the world. Korea has a lot to be proud of, especially when you compare it to a very short time scale. I remember in the 60s, South Korea was well behind in the economy compared to North Korea. And look, today I visited North Korea 2 years ago. It's two different worlds that do not exist on the same planet. So the issue is success in science, whether there is a secret for success in science. I think that there is not a recipe for that, but I think that it's composed of two elements. It's composed of an ecosystem. You need to build an ecosystem, and I think that Korea has a wonderful ecosystem for that, the universities, the education, the ambition of the people. But it requires also, I think, some type of a DNA of the people themselves. And I already talked to the dean and to previous president of SNU and to other presidents of Korean universities. And the DNA of the people is something that is very hard to learn. It's very hard to transfer, to inject. I think that the Israeli people has this type of DNA, partially because of circumstances. We are surrounded by not such nice neighbors. Your neighbors are not much nicer, but ours are even worse. And I think that the threat on our existence is much more imminent and much more realistic. You can see it daily. Syria, you see the instability, Iran, and so on and so forth. So we must be ahead of our neighbors. Otherwise, we are really lost, and we cannot rely on the United States. And I don't want to go to politics, but we need to have our own power, and that's, of course, part of the DNA that pushes us. You know, there is no choice. You know, either we are there or we are not there. But I think that there is also other part to the culture, and that's the independence and the restlessness of the Israeli society. We are very individualistic. We are very cast-doubting. We are very question-asking type of society. I think that the Koreans are too nice people. You should be less nice than you are. You know, people are obedient. They respect teachers. They respect parents, and so on and so forth. Again, this is not the secret, but I think that you must get out of it a little bit, to be a little bit, I would say rude, but a little bit more non-believers. I'm a non-believer in my character. You know, I always go and check. Whatever people tell me, I listen carefully, and then I go and check. I don't believe people, in principle. But you have to check, not in Wikipedia and not in fake news. You have to check it in real sources of knowledge. So this is another trick, of course. So I think that I'm not an advisor to Korea. Again, I'm amazed with what is going on here. But I think that, and Korea has major achievements in science and technology. I'm a big admirer of Samsung. My telephones, I change it every time Samsung is coming with a new model, I have it. So. But I think that breaking the ceiling requires more than an ecosystem. And think about the DNA, and I think that it's in the hands of the universities, and especially SNU, which is a world-leading university, no doubt about it, to think about not only the material that's being taught in the universities, and Israeli universities are not as good as the Korean one. I mean, the Technion, it's a very good university, but if you look at the ranking, we are somewhere at number 100, I don't know what we are. We don't put much attention to this anyway, but so it's not the material. I think that universities and leadership should think also on the DNA of independence, free thinking, and so on. But that's a little bit about the title. I thought about the title, the dream of the Nobel Prize. So, because it's a medical school and because I am a physician, actually I am not a scientist by education, I'm a surgeon. So I want to give you, before I go to my talk, a little bit of my own biography, so you will see how one goes from one world to another, how to choose a career, and so on and so forth. So I was born in Israel. I'm an Israeli born a little bit before the country, in 47. The country was born in 48. So actually I was born in British Palestine, what used to be Israel was part of the big British Empire, and grew up in a very poor family. The country was very poor at that time. I mean, really, and I grew into a war. So when the country started, there was a big war there. About 3% of the people were killed in the war. Think about 3% of Korea being killed in the war. The numbers are staggering. And most of the people, very few were local. Most of them were refugees that came from Europe from the Holocaust. My parents came to Israel before the Holocaust, but again, they were not local citizens. They didn't have the tradition and so forth, and grew into a regular society with very little supplies at home. Food was rationed, and my mother, I remember, had to go with vouchers to get 1 kilogram of flour and 10 eggs or whatever. But anyway, education was very important at home, and then I went to school, elementary school, and then high school. High school, I fell in love with biology, so I specialized in biology, but then I decided that I want to go to medicine. I want to become a physician, which is on the borderline of biology, of course, biological, pathological mechanisms, but also involved with the human beings. And in Israel, people have to go to the military at the age of 18. Not all of them. There are some that are excluded, but most of the people have to go to the military at the age of 18. But the military is very sophisticated. And in order to attract professionals, the military allows some talented high school graduates to go and study first, and then come and serve in their profession. So that's the way that the military gets engineers, aeronautical engineers, computer scientists, physicians to treat the soldiers. So I was among the lucky one, and I was allowed to go to the university, study first medicine, and then come and serve as a military combat physician. I went to the Hebrew University in Jerusalem, which is our capital. It's the oldest university in Israel, studied medicine. But already in the middle of my studies, I had some doubts whether what my mother wanted me to be is something that I want to be. So I was not sure that my mother will and my will are identical. Jewish mother really want their kids to be doctors. I don't know why being a physician is something that is a dream of every Jewish mother. But so I took a year off and did biochemistry, did my master in biochemistry, and then I knew that that's it. I am sold to it, but then things are changing. And after 1 year, I went back to medical school, graduated medical school, went to the military, served as a combat physician in the military, even during the wartime. And then I fell in love again with medicine. You know, loves are changing. It's something unstable. And I fell in love because the military medicine is very active. Wounded soldiers, you see action. So I fell again in love with medicine, and I decided that I want to be a surgeon. So I went to do my residency in surgery, and after a few years in surgery, again, I fell in love with the other woman, with biochemistry. So I felt that surgery is very interesting, very action, lot of sweat and adrenaline in the operating theater, but I felt that I want to understand the basics of diseases, why disease starts from the very beginning rather than treating the end result. You know, when you are seeing a patient and you know it, the physicians among you, medical students will still know, you are seeing the very end result. When you see a Parkinson patient, it's already 80% and more of the substantia nigra par compacta that has gone. When you see an Alzheimer patient, it's already, you know, the fibrils, the degeneration is already well advanced. And the same for mental retardation, and the same for myocardial infarction, when the arteries are occluded, and the same for diabetes, when all the islets of Langerhans are exhausted or completely degenerated. You are seeing the very end result. We have a huge reserve capacity. We have to degenerate 80% of our function, the same for the liver, in order to see the first symptom. The patient will present the first symptom only when 80% of the tissue of the function has done, in most cases. So I decided to go back and to do science, and I joined a very young professor that just came back from his own postdoc. He's also an MD, but didn't go through surgery, Avram Hershko, and it was kind of an adventure. I said I want to do my start and see how science is going, and I didn't even want to do a PhD because I wanted to try it first to see whether it fits me, and I had to go to the chairman of surgery to tell him that I'm leaving and ahead of time, so there will be a replacement. And he thought that I'm a little bit on the cuckoo side, and he offered me some help, but I told him that I don't need any help, or I feel that I don't need any help. But it was a process. But the point in the process was that when I approached Avram, who later on became my mentor, he told me that he doesn't know whether we are going anywhere in science, because he has an idea, because there are milestones that point, and I'll come to it in a minute, point to the existence of the system that at the end we discovered, but there is no evidence at all. So it was all an assumption. And it will be an adventure, kind of a journey. If I want to join him, typically he told me that he wouldn't take a graduate student for a high-risk project like that. But since I'm a physician and I'm always have the option, and I told him that if I'm not successful, I will go back to medicine. If I'm ready to take the risk, let's do it together. And I thought about it, and we joined, and the rest is history. So I tell you, I'm coming now to the science, but I want to draw some lessons. And then, of course, I finished my PhD. It took several years. But then I decided that, and we discovered the ubiquitin system that later on brought us the Nobel Prize. And I was offered immediately a position in my own school, in the Technion, but I decided that I want to go away to a postdoctoral fellowship to get a further training. But not only that, but I felt that if I stay, I will always be identified with my mentor. I thought that it's crucially important and fundamental that I will go to another place and build my own identity, though I had a position. So very few people will renounce a position in university in order to take another adventure, but I felt that I need to be exposed to a different way of thinking, to a different culture, to a different school. I went to MIT, and I spent 5 years at the Department of Biology at MIT with Harvey Lodish, a very good cell biologist. Now he is at the Whitehead Institute of MIT, and only then I came back. So before I go to the science, mostly for the young students here, to the young medical student, I remember the day that I was a medical student, so I have a lot to share with you. I'm not coming from an ET, from a different planet. It looks like simple, okay, you make a decision and so on, but I think for you there are some lessons in the story that I told you. And of course it's different from country to country, from culture to culture, different how you grow up. You are in medical school, I'm sure that you are very proud and the society appreciates you a lot. You are in the best leading university in Korea and so on, and you will become a very successful physician. But for me, and this is the advice for you, think about, even when you become a physician, you should graduate, of course you should graduate and make your residency and so on. Think whether you are, some of you, not all of you, are extremely happy with what you do. Because for me, it was type of a feeling of restlessness. I felt that yes, I know medicine, I'm happy with it, I'm a good surgeon, but I'm not at the top of my happiness, that I can do something else. Not getting the Nobel Prize, 30 years ago, 40 years, I didn't even, it was not a remote dream, and you shouldn't even dream about it. But I felt that it's like, you get it in the tips of your fingers, a gut feeling, that I will be much more excited doing something else. Because many people, and the change is not a dramatic change. We are very young. In Korea, you don't even serve in the military for a long time. And we are living now, life expectancy now is very long. People at the age of 70, I'm more than 70, are quite young, in their spirit at least, and they travel all over the world, they are active, they do whatever they want to do, they are energetic. And once you are finishing medical school, you have almost 40 years of career, if not more. Think if at the fourth decade, once you are entering after 10 years and 20 years and 40 years, you are still as happy as at the beginning. That's the trick in life. The trick in life is not, okay, now I'm a physician, I'm a young physician, and this and that. The trick is to ride the horse with the same degree of enthusiasm and passion 40 years later. You don't know it. Of course, you don't know how you're going to look like in 40 years, but you can have a feeling for that. And my feeling was that surgery will not keep me, uptight and happy and enthusiastic and passionate for that long time, and science will. It doesn't say that science is better. Surgery is better for many other people. I'm not judgmental. I think that the judgment should be personal. It has nothing to do with me moving from surgery to science. It can be the opposite. Your own personal feeling about yourself, what is good for you to do that will keep you passionate and enthusiastic for the long life that you're expecting. And the change is nothing. I don't think that, it's very difficult for you to grasp, but maybe for the faculty member it's a little bit different. For me, life never had a target. I never had a target in life, certainly not the prize. I think that life is a collection of experiences that you enjoy and move on. Think about, okay, you want to make $1 million. Okay, so you made the $1 million. Then you want to make the second million. And then those billionaires are dying and leaving huge fortune behind, and they have 5 apartments and 5 airplanes and 5 yachts and 5, I don't know why, what, and nevertheless, billions of dollars are sufficient for more. So it's not about achieving something and then you are resting on your laurels. I don't rest on my laurels. I have an active lab. I collaborated here. I have a very active collaboration here. I'm traveling. It's not that you get the Nobel Prize, okay, and then, okay, you sleep for the rest of your life. There is no target, I think. The idea is enjoyment and fulfillment. It's a very difficult philosophy to grasp, because now you're aiming at your MD. And after your MD, you're aiming at your residency, and then at your fellowship, and then at your expertise, and then making money. But then you will see that after achieving all that, so what? Then you have another 30 years, and then what do you do? So think about it. It's complicated to grasp, but I was always directed by my own, I wouldn't say happiness, but my own passion and enthusiasm. And just to conclude it before I'm jumping quickly to my science, is when people ask me, what is my profession, when you are entering Korea or any country, it's a profession. So of course I write scientist, physician, I don't know what I write, something. I don't have a profession, I have a hobby. So people ask me, do you have another hobby? I said, why? Why should I collect stamps if I can enjoy science day and night? I read science, I go to the lab, I talk science, I enjoy science. Of course, I'm listening to music, I'm enjoying traveling the world, seeing different cultures. But the idea is at the end of the day, and that's maybe the summary, the nucleus of what I told you, is to have a profession that is your hobby. So I don't have to go to work being bored all the day and coming in the evening and paint a little bit, or collect or arrange my stamps, or sculpt. Or it's nice to sculpt, of course. I don't tell you not to be sculptors or dancers or whatever. But I think that if what you're doing all your life is your hobby, and your university or whoever even pays you for that, what's wrong? I'm doing my hobby. My university pays me every month a check. Not too bad. So think about it seriously. It's not, I'm presenting it humoristically, but think of it, because career in science and in medicine is not a simple one. You devote a lot of effort into it, and you really want to enjoy it for the rest of your life, because this is the formative years that you are now doing. Okay, so now let's go to the science. So I think that the introduction is more important than the science, because nowadays, except for unpublished data, people don't read lectures. You go to Wikipedia, you go to the internet. So the universities are changing their roles. Instead of teaching material, you teach way of thinking rather than material. Material you can find anywhere in the world. You can find reviews, and everything is on the internet. There is nothing that is not on the internet. So this is my city, the city of Haifa. The medical school is this white building here. It's not part of the university, like SNU campus is not here. The medical school and the hospitals are here. In our case, it's exactly the same. The medical school is next to the big teaching hospital. It's a big comprehensive tertiary hospital, and it's here, and the campus of the Technion is on the mountain. And on the back, it's a beautiful city that sits on the bay. And the issue was proteins, and how proteins are destroyed. And it's very interesting. If you have to really think of life has, in my opinion, it's again a concept. It has a longitudinal dimension, which is the DNA, or the genetic material, how we transmit characteristics from generation to generation. And it has the horizontal dimension, which are the proteins, the machines on which we are running. We are not running on our DNA. We are running on our proteins, and proteins are being synthesized. So this is, for me, the slide that encompasses, encapsulates life in a very simple way. We are taking two amino acids and we bring them together, and then another one and another one and another one by taking out a molecule of water. Of course, the process is not random. It's all based on the genetic code, the specific amino acid. And then we have to destroy them. So we have to introduce the molecule of water and destroy them, and the processes are very different. It's not reversible. It's not the same process at all. So the question was about the destruction of proteins. And already here, we chose something that we knew is not in the mainstream, is not on the highway of science. At that time, we knew that people are interested in protein synthesis at that time. The central dogma of biology, DNA to RNA to proteins, Watson, Crick, Alex Rich, all these big guys. And we went to the other side that we knew is not attracting too much attention. Because destruction in principle is not something that people are interested in. When you are in a small country, you have to calculate your steps in order to make something that will be significant. And we went to protein degradation. If you think of protein degradation in the body, it's a stepwise. We are destroying proteins, of course, in the gastrointestinal tract. Our diet in Korea, you enjoy a lot of meat, so you have to destroy all the muscles of the meat that you are eating, the actin, the myosin, and so on and so forth. But cheese, dairy, everything has proteins, of course, and we need to destroy them, and this is completely non-selective. Every protein that goes into our digestive tract is destroyed, completely degraded to amino acid, from which we are building our own proteins. We cannot inject to the body foreign proteins, because otherwise we shall elicit, of course, the immune response which we are using when we are using immunization against diseases, of course. So we do inject proteins in order to elicit immune response, but in the diet we cannot do. Then once we are crossing the gastrointestinal tract, we start to be very selective. When we are in the circulation, outside the cells, but in the blood, there are many proteolytic systems there, but they must be under control, because it is a destructive activity, and we should remember it. So, for example, the blood coagulation system is a proteolytic cascade. When we get wounded or something happens, we start a proteolytic cascade where one protein is activated, become a protease, the protein cleaves the next proteins, makes it active, it chops off one piece, the next part, protein becomes active, and so on and so forth. And at the very end, fibrinogen becomes fibrin and generates the mesh. Once we are coming into the cell, we are becoming even more selective, because we cannot afford by any means an active proteolytic system that will be active all the time, because otherwise the cell will be destroyed. And in the cell, there are several proteolytic systems that have been identified, but they are all under a tight control. Now, if we look at what I call the destructive map today, it's a very extensive one. And I will not go into all the details of this map, but there are three major systems that are involved in destruction in the cell. Of course, one of them is the apoptotic system, which is involved in destruction of the entire cell. We are destroying the whole cell. When we are destroying cells, we are destroying cells that are irreversibly damaged by irradiation, by a process called apoptosis. But we are destroying also cells in order during development of the embryo. For example, the fingers. There was tissue that connected the fingers, and we destroyed it during embryogenesis. And there is a defect, inborn defect, that is called syndactyly, where the fingers are fused together when the tissue is not dissolved. So, and so on and so forth. So apoptosis is a critically important process that destroys the whole cell, but only damaged cell. So it must be selective. It must select the damaged cells from the healthy, normal cell that neighbors it, and also for destruction of, for differentiation and so on and so forth. Then, of course, there is the, how do I remove this, I don't see the, okay. Well, okay. Then there is the lysosome. And the lysosome developed in two stages. Initially, it was discovered by Christian de Dive, the late Christian de Dive, as an organelle that destroys extracellular proteins that are brought from the cell from the outside, like the LDL particle that brings cholesterol, the insulin that signals the cell and then goes via the insulin receptor into the cell and being destroyed. That's the off reaction, and so on and so forth. And then it was further developed by Yoshinori Yosumi to find that the lysosome is also involved in autophagy, in eating the cell's own proteins. So the cell during stress eats itself. It's called autophagy. Phagy is eating, auto itself. And the last system is, of course, the ubiquitin system, that is the selective system that we discovered. And you see that all the systems were acknowledged by the Nobel Committee and won the Nobel Prize either in chemistry in different stages. So there were 2 Nobel Prizes for the lysosome, 1 Nobel Prize for the apoptosis, and 1 Nobel Prize for the ubiquitin system. So destruction took its place on the podium rather late, much after synthesis, but people realized that there will be no construction without destruction. So we need to destroy our proteins for many different purposes. One of the purposes is, of course, quality control. Proteins are extremely sensitive to mutation, to denaturation, to irradiation, to whatever, and they need to be removed selectively in order not to cause harm and diseases, and we'll get to the diseases soon. So as I said, we need to remove proteins, we need to destroy proteins for quality control, we need to destroy proteins in order to control processes, like cell cycle, we need to remove inhibitors of cell cycle in order for the cell to divide, and of course we need to destroy protein in order to allow differentiation of different tissues. So the liver should have only the liver proteins and the brain only the brain protein. So of course we suppress transcription, but on the other hand we have to destroy proteins that are already generated in the embryo in order to make sure that the tissue is highly specific. And in cancer, we see dedifferentiation. We see that proteins that should not be expressed in the tissue are expressed in the tissue. So cancer is a disease that one of the hallmarks is dedifferentiation. So proteins are coming back rather than being vanished forever. So the founding father of the field was Rudolf Schönheimer. This is another part of history. I'm not going to his science, but just to show you how science is affected by politics. So the center, and it shows you also the geography and the geopolitics of science. The center of science until the late 30s and early 40s was Europe. Germany mostly. Germany was the leading superpower in science, and Rudolf Schönheimer was a Jew that worked in Germany, and of course when the Nazi came up to power, he was kicked out, fired, many were murdered. He was lucky to be kicked out and went to the United States, to Columbia University in New York, to develop his science, and so did many others that won later on many Nobel Prizes. Actually, 40 German Jews that were expelled from Germany won the Nobel Prize by being in the United States. It just tells you. And it tells you also that science and dictatorship cannot live together. You may ask yourself why. Scientists are doing animal experiments, they are working in the lab, what do they care about politics? Maybe they do not care about politics, but they care about freedom, about traveling, about conferences, about speaking freely, about inviting guests inside to conferences. Science is about freedom. And whenever freedom is suppressed, science is suppressed in parallel. You can see it in communist Russia. They still are not out of it. You can see it with your neighbors. You can see it anywhere in the world. It's almost the rule. Democracy may not be the ideal system, but it's clearly the optimal system in order to develop science. So this is really one example. And what happened to Germany, that it lost all its science, all the institutes, everything, and who benefited from that? The UK and America. America, you know, many of us got their part of their education in the United States, I at MIT, others all over the world. We are traveling a lot to the United States. America was not the capital of science until 60 years ago, and it's now losing its power. Again, why? Because of changing politics. And the weight is going back now to Europe and to Asia. China is changing. They still have a long, long way to go. Korea became a superpower. Japan became a superpower. It's moving back, again, because of political changes. Very interesting, if you think about it, even the language of science changed. Until the 40s, the language of science was German. Now the language of science is English. Everybody, in order to survive in science, needs to command English. The writing is in English, the conferences are in English, everything is in English. It became the international language of science. I hope that one day it will not become Mandarin, but who knows? You never know. I'm not going to learn Mandarin for sure, not in my age. So, but it shows you, think about it, think globally about it, what happened to science and to history of science. So Rudolf Schönheimer was the father of proteolysis. He did some experiments with labeled amino acids and found that when you give to an animal amino acid, the amino acids are going into proteins, but then coming out, and very quickly. So we are very dynamic. And just to give you a sense of the dynamism, we are losing daily, every one of us, destroying daily, and of course replenishing daily, between 5 to 8% of our proteins. 5 to 8% every day. The chemist can do a very simple experiment. You know, when we look daily in the mirror at ourselves and we think we are the same, 5% have gone and replenished with new one. This raises a lot of questions, of course, very interesting questions. If we are replenishing ourselves within a month or 2 or 3, there are proteins that are very short-lived proteins. It's an average, of course. Some proteins change themselves 5 times an hour, and some proteins change themselves like hemoglobin once in 120 days. So it's an average. But if you ask yourself, okay, if we are replenishing ourselves, why we don't remain young forever? Of course, this is an immediate question. This has to do with mutations, accumulation, and other theories of aging that I don't want to go into. The other, not less interesting question is, how is it that we are replenishing all our repertoire of machines, all our machinery within few months, and we nevertheless keep the high functions of the brain intact? I'm not talking about chronic brain diseases, neurodegenerative diseases. I'm talking about the normal person, passion, intelligence, memory, imagination. Everything is remaining intact, despite the fact that the brain, which is not an exception in that sense, protein catabolism in the brain is almost the same as in any other tissue. Nevertheless, we are keeping our knowledge. It's a very complicated question. It has to do with some theories of imprinting, the prion theory. I don't want to go into it. It's awfully complex and still debated in the field. But nevertheless, it's a very exciting question. Think about if you are changing your computer, if you are buying a new computer, which is identical to the old one, you nevertheless still have to take the software and move it to the new computer via direct, via the cloud, via whatever. Anyway, so let's move quickly. So he was the father, then came Christian de Dive and discovered the lysosome. As I said, then the lysosome is an organelle in the cell, which inside the organelle there are hydrolytic enzymes, proteins that degrade proteins, but the process is not specific. So the proteins are being taken up to the lysosome by blebbing, and you can see it here on the left side. So it sucks in blebs of the cytosol, open them up, you see it on the right upper corner, open them up, and here, and the contents are being poured in. This is non-selective because in this bleb there are millions of molecules. Most of them are healthy. So if we want to remove one molecule that is mutated and keep all the other same molecules intact, this mechanism does not give us the answer. And this was exactly the discussion that I so vividly remember when I talked to Abraham Hershko, my mentor, and he said, it cannot be the lysosome. It just cannot be. The lysosome, by all mechanisms that we know, maybe there is something else. And there were theories around. People realized that the lysosome, by this mechanism, cannot be specific. Then people thought about some channels that recognize mutated proteins by hydrophilicity and hydrophobicity. I don't want to go into all the theories, but I remember vividly that Avram told me the lysosome is highly unlikely to be the organelle that degrades proteins in a selective manner. And I want to find the selective mechanism, and as I told you, I joined this this journey. And the journey, again, I will not go into to tell you what it took, but the very beginning, because at that time there were no molecular biology technologies, we turned to nature. Luckily, both of us are physicians, so we knew what's going on a little bit in medicine. And we turned to a red blood cell, to the human red blood cell. Basically, we moved very quickly to the rabbit, but it's the same idea, to the reticulocyte. The reticulocyte is a young red blood cell, and we knew that the reticulocyte, during its maturation, to become mature red blood cells and to be ejected from the bone marrow and go into the circulation, get rid of the lysosome. So there are no lysosomes. So nature provided us with a genetically engineered cell that doesn't have a lysosome, but nevertheless degrades protein. Because we knew also that the reticulocyte degrades all its proteins and leaving very few there, leaving, of course, hemoglobin, the red blood protein that enables us to breathe, and some glycolytic enzyme to generate ATP and energy, some glutathione to reduce, to keep the reduced potential of the cell, and so on and so forth. But very few are left. So no lysosome on one hand, active degradation, so who is carrying it out? There must be a system. So we said to ourselves, okay, let's go to it. And again, people, scientists, despite the fact that they think that they are very advanced, they are as conservative as any person that you will ever meet on the street. No difference. People told us, yes, when I came to conferences before we discovered, and after we discovered, they said, it's unique to this cell, but it's not universal. Forget about it. Maybe you'll find something, but you'll forever remain in the red blood cell. I said, okay, but the red blood cell differentiation is an important process. Without it, there is no life, so we nevertheless continue. But there will always be somebody that will either turn you down from whatever reason, coming with some biological reasoning. So another advice, well, it's not an advice, of course, is to keep the background noise low. You know, to turn off all your switches and to do what you think is right. Of course, you must be reasonable and based on the literature and all around, but the background noise can really take you off the way. It's especially if you live in a small country and you go, say, oh, I was in a conference and somebody said that and somebody said that. That's the best way to be off track. So just another one. We took this one, and at no time, well, a few years into it, we discovered the system. We discovered a very selective system that degrades protein. I will not go to show you details because I want to jump very quickly. I have a few minutes left. We published the first paper in a very obscure journal. At that time, it was not obscure. It's called BBRC, very low impact factor. With that journal today, you'll never get, not a tenure, you'll never get a position in any university. Not to say in Korea, in Israel even not. But it turned out to be the most important paper that we ever published. There are other issues to this paper. This is one of the papers that was cited by the Nobel Committee, which tells you again in retrospect that it's very important what you publish rather than where you publish. But that has to do with a different lecture about our metric culture that I am not going to devote time into it. And here we discovered the system. We discovered a very interesting system that degrades proteins, you can see here. And what was very interesting is that the degradation, if you look just at the numbers, was dependent on metabolic energy. So nevertheless, in the gut, when we chew a protein, we derive energy. In the cell, we have to invest energy. It's the opposite. And the reason is to prevent destruction. Because whenever cell has to control a process, not to be destroyed, it has to invest energy. Think about pumping, all the physiologists are here. Think about pumping ions. We are keeping sodium at 150 milliequivalent outside the cell and 5 milliequivalent inside the cell. We are keeping potassium at 5 milliequivalent outside the cell and 120 inside the cell by the sodium-potassium ATPase. Once we die, immediately there is an equilibrium of all the ions, and we die. The heart pumping, the action potential of the brain are all dependent on keeping pumps that are deriving their energy from sodium-potassium ATPase. All the processes in the body, in order to keep the cellular environment distinct from the extracellular environment, again, it's a concept in biology. We need to invest energy, and so is to keep the proteins intact. When we want to destroy one single protein, we have to pick it up, put energy in, and the challenge for us was to find a system that, unlike all the other proteolytic processes that are outside the cell, does require metabolic energy. It's a distinction even from the coagulation system in the blood. The coagulation system in the blood, which is outside the cell, does not require any energy. Your gut does not require any energy to digest your diet. But in the cell, you have to put an energy in order to keep the cell intact, otherwise the cell will be dead in no time. Again, it's a general concept in biology that is only part of it has to do with protein degradation, but the rest has to do with life. Think just about ion channels. Can you imagine keeping an ion gradient of 30-fold of each on every side? And the same for hydrogen, the kidney, and so on and so forth. So we discovered the system, then we started to purify it, lots of time in the cold room. We discovered some of the factors of the system. It turns out not to be one single component, but a multi-component system. But the end of the story came in 2000, and when the human genome was unraveled, the very famous April issue of Nature, and it turned out that the system that we discovered is the biggest system in the database. It contains close to 2,000 proteins, about almost 7-8% of the whole genome is devoted to quality control in one way or another of protein, maintaining the quality control of what we call the proteome. I will just show you the principles of the system, and I want to jump very quickly to medicine and to show you how the system occupied a central role in modern drug development. So the system is the following. Here you have a target protein. Something has to happen to the protein. It has to be phosphorylated in this case, and the protein is being bound to an enzyme called ubiquitin ligase, and then a protein called ubiquitin, and the name of the system is on ubiquitin, is being activated by ATP, by energy, to a first enzyme called E1. Then it jumps to a second enzyme, and then it jumps to the substrate. And it marks the substrate. It binds covalently to the substrate, not one time, but several times to make a chain, and the chain marks the substrate for destruction. Once the chain is marked, the scissors are coming, and the scissors are called the 26S proteasome. I will not go into it, but we'll come back into it when we talk medicine. Ubiquitin, the chain is being recognized by the scissors. The substrate become closer, opened up, and destroyed. So there are two steps to the system. I will not go into it. One is marking of the specific protein that is denatured, mutated, inactivated, whatever happens to it by ubiquitin. And the second step is recognition of ubiquitin by the scissors, bringing the substrate close to the scissors and cutting it down. The secret of the system is the specificity, and the specificity is, of course, the recognition by the ubiquitin ligase. So each protein has its own ligase, not every protein, but a group of small proteins, that maybe 10, have their own ligase, and the ligases, this E3 that binds the protein and leads to its modification by ubiquitin, are the major part of the family. There are close to 1,000 different ligases in the cell, 1,000 of them, that are responsible for recognition of more than 10,000 proteins in the cell that are targeted by the system. So this is just the principle of the system. The rest is in the literature. Let me now jump to medicine very quickly. I'll skip this one. And the issue is, of course, why medicine? Why protein degradation should have to do anything with diseases? So you may think that if you think about medicine, medicine is the profession of numbers, right? If you open, I don't know in what class you are, but if you open Cecil or Harrison or any textbook of medicine, the very end are numbers, right? You need to remember blood pressure, calcium, phosphate, sodium, potassium, heart rate, anything, glucose level, anything. We just talked about glucose level, right? Anything is a number, and any deviation, major deviation from a number of most of the myriad components in the body is a disease. Doesn't matter which. Weight, anything is a number. So proteins keep their level, and if something happened to them and they are excessively degraded or somehow not degraded, we have a disease. Think about anemia when we are missing hemoglobin, or think when there is an excessive ubiquitin, the Guglielmo syndrome, when the blood becomes viscous and coagulate and cannot flow. Think about albumin, when the liver disease, there is hypoalbuminemia. Think about, there are many diseases that have to do with protein either uprising or decrease in level. So the same is for the ubiquitin system. And here you have just an example. These are all sections of patients with Alzheimer's disease. And you see that ubiquitinated protein, what is stained here, the immunohistochemistry show you constipation of ubiquitinated proteins in the brain of early onset Alzheimer's patients that are not degraded. I don't say that this is the reason for the Alzheimer's disease, but I'm saying that part of the defect in some of the Alzheimer's syndrome, because there are many causes for Alzheimer's, is accumulation of proteins that should be degraded by the proteasome and are not degraded. But let's go to cancer, because in cancer we are seeing already drugs in the market, and very successful drugs. So let's go to cancer and think about cancer again in terms of the ubiquitin system. If you have a tumor suppressor on the right side, like P53, that is excessively degraded by the ubiquitin system, then you are removing the protection of the cell by the tumor suppressor, and you may have cancer On the other side, if you have an oncogene or a growth-promoting factor, like the EGF receptor, that is mutated and not degraded, then you also, or beta-catenin in the Wnt pathway, then you also have a cancer. So on either side, if you have a suppressor that is excessively degraded, or an accelerator that is under-degraded, in principle, you are going to have cancer, and that has been described in numerous cases on each side of this equation. Let's take the right side, P53, very common cancer, human papillomavirus-induced uterine carcinoma, the HPV, another Nobel Prize to Harald Zurhausen from Germany. The HPV encodes an oncogene called E6. What the oncogene is doing, the oncogene binds to P53. It heterodimerizes to P53. The ubiquitin system looks at it and thinks that this is something strange, it has never seen it before, and as a protective mechanism, flushes it down the thing. It throws it away, degrades it, P53 is down, and cancer comes up. Basically, the virus, and there are many other mechanisms, the virus exploits the ubiquitin system to its benefits. The virus the virus doesn't care about cancer, the virus doesn't know anything about cancer. The virus is interested in replication and propagation. The virus devised a mechanism that will enable the cells to survive and to replicate in order that it will replicate and propagate. Therefore, it encodes a long evolution, it evolved a long evolution of protein that will flush down the thing, abusing the ubiquitin system, a very important protein, P53. And you can look at the other side, beta-catenin, for example, in colorectal carcinoma, in some types of melanoma. Beta-catenin is typically very down-regulated. It kept in a very low level. And if there is a mutation in the ubiquitin machinery that degrades it, will go up, will incite a whole transcription system that will elicit tumors. And there are many other, the EGF receptor, there are many other, the von Hippel-Lindau in renal cell carcinoma. There are many malignancies that are due to low degradation of oncogenes, oncoproteins, and growth promoting. Now, what about drugs? Now comes the drug. So the first drug that came to the market, and I'm going to talk only on two drugs that are very successful, and initially they were met with skepticism. Now they have saved the lives of millions of people. One drug is a proteasome inhibitor. It inhibits the proteasome, and it's used mostly in multiple myeloma. And multiple myeloma is a B-cell leukemia. I don't want to talk about it. It's a monoclonal expansion of B cells and excessive secretion of antibodies, of immune globulins. It occupies the space of the bone marrow and suppresses all other components of the bone marrow, red blood cells, white blood cells, platelets, everything is gone. Basically, the patient is hypoxic, suffering from anemia, infection, there are no white blood cells, bleeding, there are no platelets, and so it's an awful syndrome. And it turns out that by inhibiting the proteasome, the cells that secrete the B cells are undergoing apoptosis. And they're undergoing apoptosis because the immunoglobulins, some of the immunoglobulins that are being made, most of them are normal immunoglobulins, are abnormal. And if we are pushing them up by inhibiting the normal degradation, the cell induces self-apoptosis. So this is a nice mechanism because the proteasome inhibitor that induces apoptosis of the leukemic B cells is not a chemotherapy. So it doesn't have all the side effects of chemotherapy, and it's a marvelous drug. And I just want to show you, this is one of the drugs. There are already modern generations of it. It's being used all over the world. And you can see here a typical patient, or one typical patient. You see the galloping level of the immunoglobulin A in this case. It's a B cell that secretes immunoglobulin A. Chemotherapy started. You can see a partial response. Then the disease relapses. And then you can see treatment with one of the proteasome inhibitor, and it's going down dramatically. Not all patients respond. I will not go to responders. Non-responders, we can now profile them molecularly. And you can see the bone marrow. You can see on the left side the bone marrow of the malignant bone marrow, the heavy loaded. There is a heavy tumor burden of 40% versus less than 1% on the rejuvenated bone marrow. Let me go to the last drug, and the last drug is very interesting, and it's a molecular glue. This is a hit in the market now because of its potential. They are called IMIDs, or thalidomide was the precursor. Thalidomide was a drug that was used in the 60s. It was developed in Germany for women that vomited during pregnancy, a very common disease. I mean, almost every woman vomits during pregnancy, and it was a very simple drug. And very quickly, people discovered that the babies that are being born to women that used it have unbelievable teratologies, defects, mostly in the limbs. They lack hands, they lack legs, eyes in the middle of the forehead, but mostly the limbs. And the drug was taken immediately out of the market. There was a problem with the clinical trial. The company didn't report well. There was an issue of transparency of the clinical trial results. They did know about it. It was a crime, basically a crime. This was the biggest disaster ever in the pharmacological industry. There was no other disaster like that, and it was taken. And then, all of a sudden, 15 years ago, already 40 years after the drug was buried, not to be heard of, it was discovered that the drug, thalidomide, can kill B lymphocytes, mostly malignant B lymphocytes. And then it was taken out again, and it became one of the drugs of choice along with proteasome inhibitor. Now they are being used together. And for, again, multiple myeloma, and now it is being tried for other diseases. And the issue is that it's a molecular glue. And let me explain you the mechanism very briefly. The molecular glue is what we call PROTAC, or proteolysis targeting chimera. The chimera, I drew it disproportionately, but it's the yellow and red molecule. It's a small molecule of about a few hundred Dalton molecular weight. That on one hand, the yellow head binds to the ligase, to the ubiquitin ligase, and the red head binds to the green substrate, and it brings them together. The substrate and the ligase will never recognize one another unless we shall make them marry. We shall glue them together. Once the green substrate comes close to the ligase, ubiquitin will come and degrade it. So it turns out that thalidomide can bind, it has two heads. Thalidomide, you can see it here, without going into details. It has two heads, the left and the right. One head binds to a ligase that is called cereblon. The other head binds to oncogenes that drive the malignant process in multiple myeloma, among them cyclin E, cyclin D, MYC, and others. So here we have an ideal mechanism. The malignant process is being driven by the oncogenes. Now we come with the ligase. The ligase binds to the substrate that otherwise will not recognize it with a small molecule, and being flushed down the sink, and the cells are becoming healthy again or dying. Now, this is a principle, a very important principle, because now all the big pharma companies are screening for small molecules that will bind to any protein they want. They can bind to polyQ, expanded protein, in the brain, and the whole idea is to take the small molecule that binds to the polyQ or to RAS, oncogene, or to any protein. The other head is already there. It binds to the ligase, and here you have a molecule that can drive any molecule of will down for degradation. So it's not only for cancer, but the platform is now being developed broadly to many numerous other diseases. So this is really a major breakthrough in the field. Let me just tell you the very last statement of my talk, because I see that my time is completely over. And that is, medical research is awfully beneficial, though you don't even think about it. I started as a doctor, as a physician, like you will start soon, in the operating theater. Then something came to my mind. I went to study biology, didn't think of any disease, out of curiosity. We didn't discover any of the drugs that came out. It's, we just published, and then other people came, and now the ubiquitin community is a huge community all over the world. Thousands of researchers are working on it, and all of a sudden drugs are coming in back to the patient. So there is, for me, it's closing a cycle because I left the world of treating one patient by one patient, which is the world of medicine, and now I can look for 40,000 feet and see how millions of people are impacted by my own research. So I think that, think about it, it may not necessarily happen to you. You need to be also extremely lucky. But on the other hand, the world of science and technology is indeed rewarding. Thank you very much.